This week, we get to finish Chapter 3, which is really involving everything with factoring. Let's go ahead and start with Section 3.4, which is all about factoring using the distributive property. Before we can really begin with factoring using the distributive property, we have to first make sure we know what it means to even factor. So, let's go ahead and look at the definition of factoring. Factoring is basically the reverse of the distributive property. It's like you're undoing the distributive property. Let's go ahead and look at this example to see what I mean. We are going to factor 28y squared minus 4y by factoring out a greatest common factor. That's what GCF stands for, greatest common factor. So what we need to do is we need to look at our two terms and we need to decide what is the greatest common factor they both share. In terms of the numerical part, they both have a 4 as their greatest common factor, but in terms of the variable part, they both have a single y. Therefore, the GCF is going to be 4y. So if I factor out the GCF of 4y, what am I left with? From the first term, I still have a 7y. It's like you're dividing if you're pulling it out in front. And then from our second term, we just have a minus 1. Again, we're taking out the 4y. You can double check that this actually makes sense by distributing back in the 4y and making sure it matches your original expression. 4y times 7y does equal 28y squared. 4y times negative 1 is equal to negative 4y. So what is the first step to factoring? Always look for and factor out the GCF if there is one. Now, unfortunately, this is not the only way to factor. Let's go ahead and look at another approach. For this example, I want you guys to factor ax plus 4x plus ay plus 4y by grouping. Now, we technically have two different ways that we can visualize how to factor by grouping. The first would be to undo the distributive property like we learned about last week. It was the third strategy that we learned for multiplying polynomials. However, we also have that second strategy where we use the area model. I will go ahead and show both here. Let's start first by looking at the reverse of the distributive property. To do this, we are going to group the first two terms together and the second two terms together, like shown here. Then we're going to factor out the GCF of each of the two terms. For example, the ax and the 4x both have an x in common, so we can factor out an x. The ay and the 4y both have a y in common, so similarly, we can take out the y. As you can see, this is what our next step looks like. At this stage, we can actually now factor out the GCF because we have only two terms. We have our first term and our second term, and both terms have a common factor of a plus 4, so we can pull that out in front. If we pull out the a plus 4, we look at what's left from this term. We have an x remaining. From this term, we have a y remaining, so we get our final answer of a plus 4 times x plus y. Now, for those of you that really liked the area model or more of that visual representation, you can actually do factor by grouping using that as well. Because we have 4 terms in our initial expression, that means we need a 2 by 2 area model. I'm going to go ahead and draw a 2 by 2 area model just like this. Now, you want to place one of each of the terms into each of the 4 inner areas. So this is what you should have: ax, 4x, ay, 4y. Notice you could have also went down first, so you could have done ax, 4x, and then ay, 4y. That's totally fine. As long as you have terms that share a common factor in the same rows and columns, this process will work. So let's go ahead and look at our first column here. We have ax and ay. What do those both have in common? An a. I'm going to go ahead and write that up above that column because that is the greatest common factor for those two terms. If I go to the next column, the 4x and the 4y, I can similarly see what do they have in common. That's right, a 4. So we can write a 4 up above. Just like that. Now we need to do the rows, or horizontally. So the first set here is going to be ax and 4x. Those both have an x in common, so we can go ahead and write that in. And then lastly, we have the ay and the 4y. Pretty sure you guys would be able to tell me what those have in common, but yes, you are correct. It is a y. Now, where do you see your terms? Remember last week when we learned the area model in terms of the multiplication, it was the dimensions on the outside. So the base of our rectangle is here, and that would be a plus 4, and then the height is here, which would be x plus y. Notice that gives us the exact same answer that we got when we did the factoring by grouping in reverse of the distributive property. A plus 4 times x plus y, base times height of our rectangle in the area model. Now, how do you know when a polynomial is fully factored? There are two things to be sure of. The first is that it must be expressed as a product of polynomials with integer coefficients. Again, it has to be a product of polynomials, like we've been seeing. We have base times height, like in that rectangle. And it must have integer coefficients. You cannot have fractions in order for a polynomial to be fully factored. The second thing that must be true is that no polynomial other than a monomial within the factored form can be further factored. Basically, if you can continue to factor, you must continue to factor. And again, when you further factor, it has to be product with integer coefficients. I've got just a couple more examples for you. Here's your two examples. I want to know, are these fully factored? And if not, why? And please factor them. The first one is 3x squared plus 2x times x plus 5. The second one is x plus 7 times 2x plus 3x plus 21. Go ahead, pause the video, and try to answer the questions. Hopefully, you got that both of these are not fully factored. They both are not products. They have addition here, meaning that they have sums in them, and they are not just products. Then, hopefully you went on to actually factor them. Let's go ahead and see what answers you should have gotten. For the first one, hopefully you combined like terms once you distributed that 2x in to get 5x squared plus 10x. Then you can factor out the GCF of 5x to get 5x times x plus 2 in parentheses. Again, you can always double check by multiplying this back in, making sure that you get this expanded polynomial here before you factored. Moving on to the second one, you actually had two ways that you could have done it. You could have actually factored out the GCF from this second term here and then done factoring by grouping. That would have definitely worked. In fact, that's what I'm going to do here to show you. So if I factor out the GCF of 3 in that second term, you can see here that I now have a GCF of x plus 7 in both of my two terms. So I can go ahead and pull that out in front. If I do that, I'm going to get x plus 7, and then times, I still have a 2x from my first term, and then I have my plus 3 left over from my second term. So it's going to factor nicely to that. X plus 7 times 2x plus 3. And that would be your final answer. Nice job.